Okay, the next section that we're going to talk about is the rates of change. So basically the idea behind rates of change is that we're going to relate the derivative to more everyday problems. So this is going to be a lot of word problems, but it's more what is the rate of change when something's happening instead of just finding the derivative of a function. So whenever you see the term rate of change, in your head what you want to think is either slope or derivative or anything related to that. So these are all the same thing. A rate of change is talking about the derivative at a point. Also instantaneous rate of change, that's what we want to think of. When we say rate of change from now on, what we mean is instantaneous rate of change. So rate of change, in your head you want to think slope, derivative, instantaneous rate of change. These all mean the same thing. What are the units of the derivative? Let's think about that for a second. And that's how we can kind of relate this whole rate of change idea. So the derivative is always whatever f of x is measured in divided by the change in x. So it's delta y over delta x, which is the slope. This is the change in y over the change of x. So some examples of that would be something like miles per hour, meters per second, feet per second, feet per minute, something like that. So this is giving the idea that the derivative is talking about a rate of change because it's some measurement over some other measurement. So in general, that's what we're going to think for rate of change. So let's do some examples of what we're talking about here. Example 1, let's do what's the rate of change of the diameter of a circle with respect to the radius. Here we want both to be measured in inches, so measured in inches. Okay, so we're looking for the rate of change of the diameter of a circle with respect to the radius. So go back to when we were doing derivatives. Whenever we said df dx, that was the alternative notation for this, what did we mean by that? We meant the change in f with respect to x. So this meant change in f, and the bottom part meant with respect to x. Okay, in this problem, we're looking for the rate of change of the diameter with respect to the radius. So in our problem, we're looking for the change in the diameter with respect to the radius. Hopefully we can see that that's what we're looking for. So in general, the notation is df dx, meaning the change in something with respect to whatever's in the bottom. Our problem is asking for the change in the diameter with respect to the radius, which means we need to find an equation where it's in terms of the radius and it's equal to the diameter. So let's relate the diameter to radius. What do we know about the relation between the two? The diameter is 2 times the radius. Okay, now again, we're looking for the rate of change of the diameter, we'll say dd, with respect to r. That means take the derivative of this equation with respect to r. So now r is kind of like your x used to be. So using the power rule, the power here was 1. Bring down your 1, so 2 times 1 is 2. Subtract 1 and you just get 0 for your exponent, so 2 overall. What are the units here? So what is diameter measured in? That was inch. And what was radius measured in? That was also inch. So what this tells us is that in terms of the radius, the diameter is changing at a rate of 2 inch per inch. So every time the radius changes by 2, the radius changes by 1, the diameter changes by 2. So if you want to think of it as a fraction, you can think of 2 over 1. So this is saying for each increase of 1 inch of the radius, my diameter is increasing at a rate of 2 inches. So that's what this is meaning, is that the rate of change of the diameter with respect to the radius, we took our derivative and we got 2 inch per inch. That says that the diameter changes 2 inches every time the radius changes 1 inch. So that's kind of the idea behind this rate of change, is we're not necessarily looking for df dx anymore. Now we're looking for d something d something. Let's do another example of this. Let's say that a cube is expanding over time, and the volume, which is being measured in cubic centimeters, is given by V of t is 3t squared, where t is in hours. And we're gonna ask two questions. First question is, how fast is the cube expanding? So how fast is the cube expanding when t equals 4? So after 4 hours, how fast is the cube expanding? So let's think about what are we actually asking for here? How fast is the cube expanding? That's saying what's the rate of change of the cube? So how fast, how slow, what's the rate of change? Those are all the same question. So we're saying what's the rate of change of the cube whenever t equals 4? So rate of change, you want to think derivative. So what is v prime of t? Well, using your power rule, this is 6t. So if I'm asking how fast is the cube expanding when t equals 4, that means what is the rate of change whenever t is 4? So v prime of 4 would be 6 times 4, which is 24. Now let's think about units. Remember, the derivative here is dv dt. So what was v measured in? That was centimeters cubed. And what was t measured in? That was hour. So the rate of change is 24 cubic centimeters per hour. And that's how fast the cube is expanding. Second question we could ask is, how fast is the cube expanding when the volume is 27 cubic centimeters? So again, we're asking how fast is it expanding, so we're looking for a rate of change. So we're saying, what is v prime of t? We already found that was 6t. The question now is, what do we plug in for t? The question says that the volume is 27 cubic centimeters, but I can't plug in 27 cubic centimeters. That's a volume. The derivative is given to us in terms of a time. So how do we figure out the time? We set 27 equal to v of t, which was 3t squared. Okay, so divide both sides by 3, I'll get 9 is t squared, so t is equal to 3. So saying how fast is the cube expanding when the volume is 27 cubic centimeters is the same question as saying how fast is the cube expanding when the time is 3. This is exactly the same thing, because we solved when is the volume equal to 27, that was when time is 3. So what is the derivative at 3? 18, and we already found the units. That was cubic centimeters per hour. Alright, so those are some examples of how we're going to incorporate rate of change. Again, when you think of rate of change, think derivative. We're talking about how fast is something growing, or what's the rate of change, or anything like that. What's the slope? What's the instantaneous rate of change? These all are asking the same question.